All right, so this video is going over Unit 5 from our units, and just like I said in all the other units, this might not be everything we saw in Unit 5, but it will be kind of as much as we can in a short video to go over Unit 5 stuff. So remember, Unit 5 was all of our hypothesis testing. And so we had different types of hypothesis testing depending on what information we were given, how much of a population we were considering, etc. So we saw this during Unit 5. It's the same thing, just depending on what you were given and then how many populations you had, what kind of tests you needed to run, and what those conditions were. And then we had the last set, the chi-squared test, and I wrote out the null and alternative hypothesis for each of those. Remember, they're the same every time, depending on which test that you're running. And so really, remember, your conditions are given to you on the test. Just don't forget you need to figure out which test you're running and then how to run it. In this video, I'm not going to go over the conditions as much. I'm just going to talk about what the null and alternative hypothesis was, and then run the test and kind of come up with the results. So if we look at that next page, yeah, for each of these, we'll just talk about what kind of test and then run the test and see what our results are. So according to the Washington Post, 63% of college students receive some sort of financial aid. We claim that more than 63% are receiving financial aid, so we collect a simple random sample. Is there evidence to support that the claim is that more kids receive financial aid? So the original proportion, or P naught, is that 63%. And so our null hypothesis is that it equals 63%, and then our alternative hypothesis is that it's greater than 63%, because that's our claim, is that it's more than 63. So then this P naught has to do with the original amount, what our claim is, and then our sample gives us the rest of our information. So N is 200, X is 185. So then we're going to run, right? We're talking about a proportion here. We have one set of data. So this is our one prop Z test to figure out what we get. So we'll go ahead with our calculator, stats test, one prop Z test. So our P naught is 0.63. That's part of our claim. X is 185, N is 200, and we're claiming that it's more than 0.63. So our Z value is 8.64. And then our P value is 2.82 times e to the negative 18, meaning there's 17 zeros ahead of that. So no matter what our significance level, we're going to reject our null hypothesis. So we're rejecting the null, which means we have sufficient evidence to support the claim. So we can support the claim that more than 63% of students are receiving financial aid. All right. Looking at B, U.S. News did a study and concluded that students spend an average of 3.5 hours of homework each night. Cherokee Schools claims students are spending less time than that and decide to conduct a study. A random sample of 85 high schoolers in the district concluded that the average time spent on doing homework each night was 2 hours with a standard deviation of 1 hour. So, yes, we're given a mean and a standard deviation. So in this case, we surveyed 85 high schoolers. Our mean was 2 hours and our standard deviation was 1 hour. Our null hypothesis is that the average equals 3.5, and then our claim is that it is less than 3.5. And so our mu naught has to do with that 3.5. That's part of our claim. Yeah, remember that this is all part of your claim, and then this is part of the sample that you took. So because we're given a mean and standard deviation, and we're only given it of one type of data, then we're running a t-test. So stat, go over to test. I'm running a t-test. I'm putting in statistics. So my mu naught is 3.5. My mean is 2. Standard deviation 1. N is 85. And I'm saying that it's less than. So when I calculate, I get that t is negative 113.829. P is actually 0. Yeah, so that's even less. All these ones where we had a bunch of different decimals, it's way lower than that. So we're going to reject the null hypothesis, which means we can support the claim that students are spending less than 3.5 hours doing homework each night. All right, on to the next one. In a random sample of 80 men, 54% said they go to the doctor regularly. In a sample of 200 women, 70% said they go to the doctor regularly. Test the claim that the proportion of men who go to the doctor regularly is less than the proportion of women. So if we make men P1, yeah, so their N value is 180. Their P value is 54 or 0.54. So to find X, we would do 180 times 0.54. And we get 97.2, which will round up to 98. And then we'll do women, which was 200. And they say that theirs is 70% of the doctor, 70% go to the doctor regularly. So if I multiply that together, I get 140. So now, right, my null hypothesis is that my P1 equals P2. And then my alternative hypothesis is that P1 goes to the doctor less than women. And this would be my claim, is that men go less than women. So now, because I have two sets of data, they are proportions, right? So this is a two proportion z-test. So when I go over to test, I'm running a two proportion z-test. My x1 is 98, my n is 180, my x2 is 140, my n is 200, and I'm claiming that P2 is greater than P1. So I get that Z is negative 3.129. My p-value is 8.75 times e to the negative 4, which means we're going to reject the null here too, which means we have sufficient evidence to support the claim that the proportion of men who go to the doctors is less than women. All right. This was our t-test, one proportion. This is our two proportion z-test. All right, so if we keep moving on, looking at a couple more examples. Leapfrog claims that their program helps students learn to read. We took a sample of 15 5-year-olds and recorded how many words they could read before and after the program. Results are given in the table below. Test the claim that Leap improves reading skills. Assume the data is normally distributed and from a random sample. So the first thing we're going to do is find the difference. So we subtract straight from before to after. So this would be -1, 0, 1, -3, -2, -1, 2, -1, -2, 0, -1, -3, 2, 0, -1. So this is still a t-test because we're actually only now going to look at this data. And our null hypothesis is that our mean is equal to 0. Now, our alternative hypothesis, if they learned more words, right? Learning more words gave us a negative number. So learning more words would mean we'd have a less than 0 value is what we're looking for. And that's the claim that they're making here, is that they learned more words, so then our mean would be less than 0, right? Because all of our more words came out as a negative answer. So this one, we're going to put all of our information into a table. So we're going to put this all into list 1. So -1, 0. Oops. Mess that up. Okay, so we put in our 15 values. So then when we run our t-test, we don't need much of our information before because we're going to tell it to pick out of the data of list 1. Our mu naught is 0, right? That it made no difference. And then our claim is that it's going to be less than. So then we'll calculate. We get that t is negative 1.67. P is 0.058. So I don't have a significance level, but remember we usually use the significance level 0.05. If you choose to use 0.1 here and you reject, that's fine as long as you're consistent with your answer. Here though, I would say that I would fail to reject because this is bigger than that. So then there is not, right, I'm going to keep this, which means there's not enough evidence to support the claim that Leapfrog helps students learn to read. All right. So then the last one on this page, Fashion Network claims that men own more shoes, that should be shoes, not shows, shoes now than women. To find out if this is true, a simple random sample of men, man, I did not spell well in this last example, guys, sorry. Men and women was taken and the statistics are recorded below. So the fact that you have a mean and standard deviation should tell you that you're running a t-test. You're given 2 sets of groups, so we're running a 2-sample t-test. So we're claiming that men own more shoes than women. So our null, let's make men P1 and women P2. So our null hypothesis would be that they're equal. And then our alternative would be that our P1 is greater than P2, which is our claim that men own more shoes now than women. All right, so now I'm gonna go and run my 2-sample t-test. I'm gonna type in stats because it's not in a table. So my mean was 15.4. Standard deviation 3.8, N is 75. Mean is 14.7, standard deviation 3.5, and N value 72. I'm saying that P1, or this should be mu, I'm sorry, we're not talking about proportions, we're talking about averages. So this should be mu1 equals mu2, and mu1 is greater than mu2. Sorry about that. Same idea, just wrong, where we're using the wrong variable for that. So then I'm saying that mu1 is greater than mu2. So when I calculate, I get that t equals 1.16, p equals 0.12. So if I'm comparing that to 0.05, I would fail to reject the null. So that means I'm keeping this, which means there's not enough evidence to support our claim that men own more shoes than women. All right, so that is all of our practice in our Prop Z test and our T test. So now let's look at some examples of our chi-squared test that we may see. So remember, there's 3 types of chi-squared test: goodness of fit, test for independence, and test of homogeneity. So let's figure out which one is which and then solve. A survey of 230 undergraduate and graduate students was conducted to see whether their educational level affected their instructional preferences in person or online. The following data was obtained. Can a researcher conclude that educational level is independent of instructional preferences? So because it's asking us if they're independent, we're going to do a test of independence. So then our null hypothesis is that educational levels is independent of instructional preferences, and our alternative is that they're dependent. I would prefer you write more than this, right? You should write instructional level is independent, instructional level is dependent, but for the sake of the amount of space I have, I'm just going to stick with that. So we're going to then run our test, right? And all of these on the test, you'll have to check conditions, but for the sake of time, I'm just going to run the test. So our test of independence runs out of a matrix. So to run our matrix, we hit second matrix, and then we're going to edit matrix A. It's going to be 2 by 2. And I'm just going to type these values in, 85, All right, so now my matrix A is ready. So if I hit stat test, I'm running a chi-squared test. My observed values are in A. So I get that chi-squared is 38.05. And my p-value is 6.86 e to the negative 10, which means that we would reject the null hypothesis. So there is not enough evidence to conclude, right? If we're saying this is our claim, there is not enough evidence to support the claim that these are independent. If you wanted to find, or if I asked you to find the expected values, remember your calculator did it for you and it's sitting in matrix B. So if you hit second matrix and then choose matrix B, these are all the expected values. Just if you're being asked to find that, you know where they are: 66.23, 52.77. So those are the expected values for each of those. All right, on to the next one. Anytime Fitness wants to make sure they have the correct number of employees, classics, etc. for each day of the week, they expect that each day of the week gets the same number of members. To test the claim, we record how many members come to the gym each day. The following data was obtained. Can the claim conclude that every day has the same distribution? So we're testing, right, is our data, does our data match the distribution that they're claiming that they have the same amount every day? So first we need to figure out what that expected number would be. Because we're testing this against itself, this would be a goodness of fit test. So then H, our null hypothesis is that it is a good fit. Again, you should be writing more than me, but I'm just going over this. This is not a good fit. So then when I run my test, first I got to figure out what the number of expected people would have been. So I'm going to add up all these values first to figure out how many people are in our sample anyway. So we have 427 people in our sample. And then since we're talking about 7 days a week, we'll divide by 7. So the expected number here is 61 for each of these. So then for goodness of fit test, we go out of our list. So stat edit, we'll type our observed values into list 1 and our expected values into list 2. Okay, so then once we have that data in our list, we go over to our test and we're running a goodness of fit test. Our list 1 is our observed values, list 2 is our expected values. Our degree of freedom is 6, right? We have 7 categories minus 1. So that would make 6. We hit calculate. So this gives me enough evidence to reject the null hypothesis, which is their claim. They claimed that they get the same, each day gets the same number of members. So there's not enough evidence to support the claim that each day of the week gets the same number of members at the gym. All right, last one. Ivy League schools receive many applications, but only some can be accepted. At the schools listed in the table below, 2 types of application are accepted: regular or early decision. We want to know if the number of regular applications follow the same distribution as the number of early applications accepted. So we're looking to see if it follows the same distribution, which is our test of homogeneity. So our null is that they follow the same distribution. Our alternative is that they follow different distributions. So they're claiming that they have, right? We're seeing if they have the same distribution. So we run our test like this test, just like we do our test of independence. So we're going to type this into matrix A. So if I go over to second matrix, I'm going to edit. This is going to have to be 2 by 1, 2, 3, 4, 5, 6. 2 by 6. Okay. Okay, so I got that typed into my matrix. So then we hit stat, go over to test. We're running a chi-squared test. Our observed values are in A. That is a very small p-value. 9.796 e to the negative 91. So that is enough to reject our null hypothesis, which was our claim. So there is not enough evidence to support the claim that the number of regular applications accepted follows the same distribution as the number of early applications accepted. So I know that wasn't fully in depth of all the pieces, but we've done this. Go back and check your notes of how to check conditions and all of that stuff. But hopefully it was just a good refresher of each of our types of distribution or each of our types of hypothesis testing and how we can solve and interpret the results. Remember, your review guide is on page 247, and we'll have a lot of extra practice for you to do as well.